3, 2, 1, go. Okay, so today's topic has absolutely nothing to do with increasing, decreasing, concavity, inflection points, first derivative test, second derivative test, none of that stuff. So, is that good news or bad news?
It depends on what.
It's kind of a standalone lesson. Yeah. Put it in the bottom. So, it kind of is tangentially related to those topics.
Is that in here?
So we're calling this 3.8. I don't know how you call it. I'm just calling it tangent line approximations. Subtitle, using a tangent line to make an approximation. Alright? So we're going to draw a big graph right here. And some function that's coming along, we don't know what it's doing, but for this part right here, it's kind of parabola-ish. And as always, we're going to focus in on one point. Maybe call that C. And if you remember, sort of this whole year long, we've been going to this concept called local linearization, where if you zoom in, zoom in, zoom in, even though this is really curvy, if we're to zoom in close enough, what would this graph look like right there? It would look like a straight line, because it would be a point here, then there'd be a point here, then there'd be a point here, and if we were to zoom out, we'd see the curve, but if we zoomed in close enough, it would really look like a straight line. And we can draw a tangent line that's going to kind of come along, like that. There, so here's our tangent line. And so the big idea that we've already talked about is that at very small distances, a function, in fact, not just a function, any function resembles a line. Or in other words, to put it in engineering terms, at very small distance, any function can be modeled as a linear equation. So, or it can be modeled with a linear equation. So if this function right here happens to be y equals f of x, this tangent line would be just y equals mx plus b. Pretty much for this area all around here, the closer the better. This function can be represented by the tangent line, the straight line y equals mx plus b. Now, where are my engineers at? You two guys, or at least you're in my engineering class right now. What is good, why do we model things as other equations? Why would we want to do that? Normally we have data that kind of resembles this or whatever, maybe kind of goes up like this, and we can model that with a line. Why do we model that? What's the prediction? To make predictions, okay? To find out a value. So what we can do is we can use a tangent line to approximate the function values kind of all around here. You're like, okay, why would I want to do that? Well, you'll hold on a second, you'll find out. So for instance, if I've got maybe this point right here this is C plus 0.01, something that's really close. And now we're to zoom in that region right here. So, zooming in, the blue curve looks something kind of like this. The tangent line looks something like that. That's where C was. C plus 0.01 is just over a little bit. But if I plug that into y equals mx plus b, if I plug it into the tangent line, then I'm going to get a value right here. That's my approximation of the real value which is right there. So you said, now you can ask the question, well, why in the world would I go to all of the problems of finding the derivative and finding the slope of the tangent line and finding an equation of the tangent line just so I can plug something in over here, okay? If I want to figure out what the function value, what the real value is of C plus 0.01, I'm just going to plug it into the function, right? Okay, well, part of the answer to that is the historical reason, and that is they didn't always have awesome graphing calculators like you did, or like you do, okay? Even though also you do have awesome graphing calculators, sometimes the function itself, even for calculators and stuff, is very computationally intensive. Takes a whole lot of, and you might have some round off errors, you might have some issues with precision and things like that. So using just a linear approximation right here, you can get a really good value very, very quickly. Let me see if I can give you a real example here. Let's say we've got f of x equals, I don't know, x cubed. And so we know what that graph looks like. It's a cubic, it kind of, something like that. And what we want to find, for whatever reason, we want to find f of 4.01. Now, let's pretend like you don't have a calculator at your disposal, okay? How are you going to find f of 4.01? Cubic. 4.01 times 4.01. The 401, then you've got the 0, 0, then 4, then 0, 16. Okay, this is already a 1. 160801. Alright, there, I just squared it. Now I gotta do that whole thing again. Times 4. I don't want to mess with this at this point. Okay? It gets even crazier if it wasn't just a regular cubic, maybe it was a cubic plus a quadratic plus a linear term, so on and so forth. You can do all sorts of other calculations and computations, right? Super annoying. Could you plug this into the calculator? Yes, you could, but we're going to pretend that we don't just for the sake of argument. But what about my tangent line approximation? That's normally a little bit simpler. Let's give that a shot. So what number is really close to 4.01? 4. So here's 4.01. That's really, really, really close to 4. So what we're going to do is we're going to have a tangent line approximation with 4 as our C value. So step 1, find the equation of the tangent line at an x value close to where you want. In this case, we're going to choose 4. Alright, find the equation of tangent line. I know how to do that. Well, what formula am I going to use to write an equation here, Gabriella? Point slope form. Read it off to me.
y1 minus y equals m, which is x minus x1.
Yes. No, that's fine. That's me. Okay. So the point here happens to be 4 for the x. I'm going to need to figure out what the y is. So the y value is 4 cubed, which is 4 times 4 times 4. 64. So this point right here is 4, 64. It's not to scale. So y minus 64 equals, hold off on the slope, x minus 4. The slope is the slope of this tangent line. So the slope of the tangent line evaluated at 4 is f prime of 4. So alright, let's figure out what f prime is. F prime, we actually finally get to do some calculus here. Take the derivative of x cubed, 3x squared. So f prime evaluated at 4, 3 times 4 squared, so 3 times 16, 48. And then what I'm going to do is I'm going to solve this for y. So I have y equals 48x. Somebody, real quick, will pretend like we have a calculator. What's 48 times negative 4?
No calculator.
Or no calculator, fine. 96 times 2, 182. And then add 64 to that. It's 192 plus 64. You have a calculator, please. Negative 128. Okay, so there's the equation of our tangent line, which is really close to where we're going to go. Now let's plug in 4.01, not to the original function, but to our tangent line approximation. So I might say y of 4.01 equals 48 times 4.01 minus 128. Anybody? You can use calculator for that. Okay, so we're saying that f of 4.01 is approximately 64.48. Now before you do this, let's make a decision. Do you think that this is an overestimate or an underestimate? Why do you say under, Levi?
Because the tangent line is under.
Yeah, because the tangent line is underneath. 4.01 is gonna be right here, so it's 64.48. The real value is probably gonna be a little bit higher. Now, so we're gonna say this is an underestimate. Let's actually plug it into the calculator. What is 4.01 cubed exactly?
64.48120.
I think we did pretty good, don't you?
Yeah.
Without a calculator, except for the times we said use a calculator. Okay. So you got 64.48 versus 64.48120. So I mean, we are accurate to a 100 at least, and we're even just off by 1,000. So I feel like that's pretty good for just using a calculus approximation. Okay. Does anybody have any questions about what we did there? Do you understand why we're doing this? Kinda, sorta? Doing the, okay, well, at this point, that's pretty much it. We're doing tangent line approximations. There's really, at this point, we'll do one, maybe two more, talk about maybe a general rule about overestimates and underestimates, and that'll be pretty much it. Okay? So, let's do something else. Do you all want a radical or a trig function? Trig? Y equals, let me just do y equals sine of x. Okay, so let's pick a point next to a point that is kind of beneficial. Maybe, let's see, so there's pi over 2. What's pi over 4? So let's calculate, what's pi over 4 approximately?
1785.
175? Okay. Let's say that I want to find, so I want you to approximate f of pi over 4 plus, I don't know, some really, really small increment, pi over 10. So pi over 10 would be like 0.03 or something like that. 0.0314 actually, exactly. Okay. I only wrote one step down here, I guess, but I probably should have written the other one. So, find the equation of the tangent line, then step 2, plug in, yeah, your value. So plug in your x value. That's pretty much it. It's just a 2-step process. So pi over 4 is right about there. The tangent line is going to look like that. It's really helpful if we draw the tangent line because that will give us a reality check on whether or not our slope should be positive or negative. So here we go. Y minus y1 equals m parentheses x minus x1. Right? The equation of that tangent line in the form y equals mx plus b. So obviously a point that is really close to pi over 4 plus pi over 10, we're going to analyze at pi over 4. That's going to be our c value. So pi over 4, comma, what's the sign of pi over 4? Root 2 over 2. So we have y minus root 2 4. So the slope is the slope of the tangent line, which you know as the derivative. So it's the slope of the tangent line evaluated at power 4. So first off, find the derivative. Fx is cosine. So f prime at pi over 4 is cosine of pi over 4, which is root 2 over 2. I guess I maybe should have picked a more interesting one, but that's okay. So root 2 over 2. So my new formula for my tangent line is y equals root 2 over 2 times x minus pi over 4 plus root 2 over 2. They say, Mr. Goddard, why don't you distribute that and do all that other stuff? And the answer is, well, sometimes we don't want to distribute it because then we'd have to combine this square root and the pi and things like that. And I've got a feeling maybe if we keep it just like this, our answer might be a little bit nicer, or maybe not. We gotta figure this out. So we've got an equation. Step 2, plug in our x value. So y equals root 2 over 2. I'm substituting in the x that I'm approximating, which is pi over 4 plus pi over 10 minus pi over 4. So see, I told you some neat things would happen.
Wait, what?
The x value is pi over 4 plus pi over 10. The special value, like over here it was 4.01. I could have written that as 4 plus 0.01. That's kind of how I'm writing this one. I'm writing it as pi over 4 plus pi over 10. The reason is that we end up with that. Those pi over 4s cancel. And now we have a decision to make. Do we want to multiply all this out and get a decimal approximation, or maybe just leave this as y equals root 2 over 2 times pi over 10 plus root 2 over 2. You could factor that out. You could, if you wanted to, you could say it's root 2 over 2 times pi over 10 plus 1. But that still doesn't get us, we want a numerical answer. So let's go ahead and type all that out. What is that? Give me several digits, at least 6 of them after that. So it's going to be 0.7, probably. 0.79 maybe, I don't know. We need at least one person to type it in, or get an answer, another person to verify it. Point what? Oh, it's 0.9?
0.929.
9295, you say?
25.
Okay. Now, before we actually figure this out, do you think this one is an overestimate or an underestimate? Overestimate. Why?
Pi over 1 plus pi over 10 is going to be a little more than pi over 4.
Well, yeah, of course, pi over 4, but that's just the x value.
I guess I'm good.
Right, but there's no, yeah, okay, you're saying that, yep, it will be a little bit higher. But I don't think, here, Shane, I'm going to zoom in here. The original graph looks like this, okay, at that point. We've just done a tangent line approximation that looks like that.
It'll be higher on the graph and it'll be flatter, like.
It will be higher. It'll be higher on the graph no matter what. The question is, what is the relationship between that approximated value and the real value? And the answer is still, it's an overestimate, but not just because the function is increasing, okay? Because over here, the function was increasing, but we had an underestimate. Does that make sense? So here in a second, we'll answer the question generically. How can I always know whether or not I'm going to get an overestimate or an underestimate? Because you may not even have the graph, but you can still get that. So we're guessing that it's an overestimate. What is exactly, calculator in radian mode, the sine of pi over 4 plus pi over 10? Point
0.891.
Give me 4 digits. We always want to have at least 4 digits for the
0, 0.
0, 0, okay. At least 4 digits for the AP test, remember that. Okay, so we said it was an overestimate. Were we correct? Yes, we were correct. Okay, so we've done 2 tangent line approximations. One which was an overestimate, one which was an underestimate. Question is, what determines whether you're going to have an overestimate or an underestimate?
Concave down and concave up.
Concave down or concave up, very good. Let's think about that. So, concave down would look like this. Concave up, obviously, up like a cup. While I take attendance, draw some tangent line approximations all over those, as well as all over these down here. Draw some local linearization tangent lines. There you go, good tangent line.
Oh, okay, I see.
Okay, so when your function is concave down, where are the tangent lines? Okay, concave down. Where are the tangent lines in relationship to the function? Above. So concave down, your tangent lines lie above. Everywhere, whether it's concave down increasing or concave down and it's decreasing. Tangent lines are always above, and because of that, your approximations are always going to be overestimate or underestimate. Always going to be an overestimate. You're like, I'm not sure I believe that. Well, let's look over here. If we were to extend that line, this one right here, notice at any point, this right here, this x value is, this y value is above that y value. This y value is above that one. Even if I go over in the negative direction, this one's above, this one's above. I pick extend out a tangent line over there. For any given x value, the y value here along the blue line is going to be greater than the actual value. This is bigger than this. This is bigger than this. Always like that. And in the same way, if you're concave up like a cup, then your tangent lines are always under or below, I'm just used to saying below, so I'm going below the function, and your estimate is always going to be an underestimate. Okay, so I guess I was misdirecting you when I said that we're not going to talk about concave up and concave down. We did talk a little bit about that. What that means is, well, let me ask you this. How do I know whether the function is concave up or concave down? Second derivative. So therefore, if I look, not look at the second derivative at, we'll say our C value, which is our principal value there, okay? Then that will tell you, and I should say look at the second derivative, I should be more specific. Look at the sign, S-I-G-N, which means plus or minus, of the second derivative at C. That will tell you if you have an over or underestimate. Alright, and just to bring this home here, let's look at this problem right here. The very first one we did, f of x equals x cubed. So f of x equals x cubed. First derivative was 3x squared. What's the second derivative? 6x. What is the second derivative evaluated at our principal value c? That is 4. 6 times 4, which is 24, which is greater than 0. Okay? So that means it's concave up, which means concave up, the tangent lines lie below, which tells us that we have an underestimate, which is what we had concluded as well. For the sign, f of x was sine of x, f prime of x, cosine of x, f double prime of x. What's the derivative of cosine? Fix that equal sign there. Negative sine of x. Evaluate the second derivative at our principal value c, so at pi over 4. So negative the sine pi over 4, so
negative 2 root 2.
So negative root 2 over 2. Of course, that's less than 0. That tells me that it's concave, that the original function, rather, is concave down, which means that the tangent lines were above, which tells me that I'm looking at an overestimate. If I get it back there we go, overestimate. Yep, that's what we agreed. Okay? Alright, does anybody have any questions about this? Alright, I need to know at least 3 things that we talked about today. Overestimates, underestimates. Somebody else. Tangent line approximations of a function. Anything else? Local linearization. We'll talk about that. Zoom way in, everything looks like a line. Alright. Your homework I will give to you now.